Hi everyone, and welcome to my screencast on irrational guards are sometimes needed. This is joint work with Mikkel Abrahamsen and Anna Adamczyk. This is me, and the three of us, we are meticulously guarding this polygon. You might think this is a little irrational, and you're right. However, as I'll show you, it's pretty optimal. And what exactly I mean with this, you will learn in the next 2 or 3 minutes. Okay, so let me start with this talk with a definition of the problem. So it's about the art gallery problem, which was introduced by Victor Klee in 1973, and he asked how many guards are needed to cover a polygon with n vertices. That's a polygon with n vertices, and for instance this guard here, or this point, it would cover that region because the line segment for each point in this region and the guard is fully contained in the polygon. So this is kind of what you would imagine me to see, right? And then together with these other 5 points, these 6 points together cover the whole polygon. But he asked how many guards are needed. So are they really needed? And you can see the blue guard is not needed, and these two guards are also not needed. They can be replaced by another guard. And now we have 4 guards, and these 4 guards, they cover the whole polygon, and they're also really needed because there doesn't exist a guard who can see 2 of those crosses simultaneously. This, as we have 4 of those crosses, it means we need 4 guards, meaning 4 guards is optimal. So that's the art gallery problem. As he introduced it, and there are various questions you can ask about it and various variants that exist. But let me point out here one specific thing. So the way that Victor Klee asked it originally is he said the guard could be any side, anywhere inside the polygon. In the example that I showed you, the guards were always at the vertices. In order to distinguish these 2 variants, at some point people called the actual art gallery problem the point guard art gallery problem, or something like this, or interior guard. So, but for the remainder of this talk, I will only be focusing on the point guard variant. So what has been shown for the art gallery problem? Well, a lot of people showed NP hardness, hardness of approximation. With Edouard Bonnet we showed W1 hardness, but none of those guys showed NP membership, where usually NP membership is the easier thing, right? So what do we know about NP membership? Well, nothing. We don't know if the art gallery problem lies in NP, and I'm a little bit annoyed by all these authors here, never mentioning that we don't know this. Usually NP membership is the easy thing. They couldn't show it, they didn't say anything about it. 1991, we knew for 2 guards, it's in a P because Bellevue showed an algorithm with 2 guards. So before 2006, we didn't even know if the problem is decidable. And then in 2006, Micha Šerić said, oh, you know what, uses algebraic machinery, it's obvious. There's an N to the O of K algorithm. And so for any fixed K, this problem lies in NP. Subsuming the result of Bellevue. Yeah, but this doesn't show NP membership because we would need to have a polynomial algorithm for even if someone gives us cards. But this just shows there is an algorithm at all. Or it actually was pretty good running time in terms of K. If you compare to it was not known if the problem was decidable at all. Yeah, but it's pretty, there's still a big difference. So then regarding approximation, and before 2016 it was open whether there exists a polynomial time approximation algorithm. With Edouard Bonnet, I could show that actually there exists an approximation algorithm. Now we know approximability. So there are very few algorithms, and none of them enlightens whether we have NP membership. So it's still open whether a problem lies in NP. So how could you show the problem lies in NP? Well, you could try to guess guards, right? So let's guess guards, and then we check if these guards cover the whole polygon. But as I mentioned to you earlier, the guards do not need to lie on the vertices, but they might lie anywhere in the interior, right? And it's not clear how we could describe the position of the guards because we need polynomial-sized witnesses. Okay, here we check them. Let's cover. And maybe we, if we would know at least that these guards are rational, we could hope that we can find witnesses. We can describe those guards with rational coordinates, and maybe we have bounded size of the length of the integers we need. That's reasonable, right? So Shandor-Fekete was the first to notice it's not clear. We need to ask this question explicitly. We need to raise attention to this. And he asked, are there always irrational guards? He asked it first in MIT 2010. He later repeated in 2011 at Dachstuhl. Günther Rothe repeated this question at EuroCG 2011 in Mosbach. And then recently it was also mentioned in some papers as one of the major open problems in the Odd-Gilroy problem. Anyway, so this problem was asked, and up to now we didn't have an answer, and we contribute to this line of research by showing it's not the case. No, they are not always irrational. They're always rational. So we give you this polygon here, which I showed you on the title slide, and it needs 3 guards at irrational positions, and if you want to cover it with rational guards, you need 4 guards. We also extend this result slightly to orthogonal polygons. Note that this polygon here on the top is monotone. Yeah, so that's our result, answering an open problem asked by various people, which, if answered positively, might be an important step towards MP membership, but we give a negative answer. Okay, so now for the remainder, I want to prove you this result. Okay, so the first tool, which is already kind of standard, we can force a guard to lie on a line. How do we do this? We create this pocket here such that in order to see this point B, we need to be somewhere in this triangle region, and in order to see this point T, we put another pocket here, we need to be somewhere in this triangular region. Thus, if we want to see this point and that point simultaneously, we need to be somewhere on the line. And this is kind of what we mean by we force a point to be, the guard to be on that line. So we do this 3 times, and then we force a guard on this, on that line. And note that these regions here, they're all pairwise disjoint, otherwise this thing would not work. Okay, so this is that. We can force guards on lines. That's the first trick we need. The second trick we need, we want to force guards on curves, ideally. Well, we cannot do that, but we can at least force guards to be on the left of some curve. And we don't have full control how this curve looks like, but at least we can do it for some curves. So the statement here is, if there is a guard on the left of C, then we can find a placement of a guard on this blue line, such that these 2 pockets are guarded. And if the guard is to the right of C, no matter where the guard is here, we are not capable of covering these 2 pockets. So that's the statement. And now I show you the statement. It's a simple proof. I think many people know this. I've never seen it explicitly, but I think people knew this. Okay, so we start with some basic observations. So let's say we have a guard G1 here. It sees part of that pocket, and it sees part of that pocket here. And what happens if we move G1 up? Well, it sees less of that top pocket, as you see here, but more of the bottom pocket. And reversely, if we move G1 down, it's the opposite thing, right? So moving G1 up and down leads to less of the top, more of the bottom, and vice versa. So this is the basic observation for G1. So basic observation for this other guard on the right, we call G2, is if we move this guard to the right, it'll see less of the pockets. And this is pretty obvious, right? So you see this visibility cone, you see that visibility cone. Being to the right means we see less of those two pockets. Actually, strictly less. Okay, so now what we want to show is if we're inside this triangle region, then this guard can see together with this guard everything. If we're to the right of it, we cannot. So here it's pretty obvious that we cannot, so we assume here G1 being fixed, because either on the top or on the bottom there would be some part we cannot see, and if we're inside we can see everything. So now I'm ready to define you C. C is the locus of all of this intersection points I. So we look at all positions of G1, and each position gives us an intersection point here, and if we take the union of those, we get a simple curve C, which is even x monotone. Okay, I will not prove this, so I forgot that I said it. But what I want to show you now is if we're to the left of C, we can see it. Then there's a placement of a guard on this line that the two guards together see two of those pockets. So how do we do this? So we project this guard on the curve C. So now it sees less, right? So we are on a more difficult situation. But by the definition of this curve C, there exists a guard placement here such that these extension lines meet exactly here. And then these two guards can see exactly these two pockets. In particular, if these two guards can see it, then also those two guards can see it, because this guard sees strictly more than that one. So now let's say we are outside or to the right of C. Then, okay, we again look at the projection towards C, the orthogonal projection. And what's happening is now that this point here and this point has a point on the line, on the blue line, such that together they see everything, or the two pockets. But at this point here is to the right of C. This point sees strictly less on the top and on the bottom. And now could this guard compensate for what is not seen here and there? And the answer is no. Because let's say we look at some positions of the left guard to the top of this brown position. Well, it would see more here, but it would see even less there. So meaning if we look at any position on top, we cannot expect to see this. And by the same argument, if we look at any position below this brown region, then we see less here, and meaning that we cannot compensate this. So altogether this shows if we are on the right of C, we cannot expect any placement on this blue line such that these two guards together see the two pockets. Okay, so now I showed you the statement that I claimed in the beginning, and now I want to use it. So let's look at the whole polygon again. So we forced one guard on this line, we forced one guard on this line. So this line here, together with these two pockets, forces us that there must be a guard to the left of CL, and in a similar fashion, this line together with these two pockets forces us a guard to be on the right of CR. Okay, so this means that the region where I need to place the guard is this brown region, which is bounded. So the boundary is part of the gray region. Okay, so let's take this for granted now. There's a subtlety which I will explain in a second, but take this for granted. Then we can compute this intersection point of these two regions, and we put a line through it. So we forced a line on this, we forced the guard to be on this green line, but this guard GM, it must be on this green line, it must be to the right of CR, it must be to the left of CL. So the only possible placement of this garden is exactly here. So with some computer algebra system, we can compute these two curves CL and CR, and there's an intersection point, and we see that's the intersection point, and it's irrational, and that's the only possible placement. And that's the end of the proof. Right? Pretty simple. You only need to compute that. There is some subtlety here. That's why we need those three pockets. So it could be that GL and GM are not seeing together these two pockets. However, GR might help us. Right? Or it might be that GL helps to see those two. It looks unlikely, but in order to prove it rigorously, these three small pockets are very helpful. I don't think they're really needed, but they're pretty helpful, so we use those three. And yeah, that's the proof. Minus this detail on how we use those and this computation here, and that GL can't help for those. That's the proof. If you want to do the computations, this is Sage code. Yeah, you can try it out. The same for this compute CL. The same you can do to create CR. You have to plug in the coordinates you can find on the paper. Yeah, so the question is, how did we find this polygon? It looks like we didn't do much, right? But actually we did a lot. Or at least it was really non-trivial. So let's assume we have some random polygon. So I want to show you why we needed to use a specific polygon that I showed you, and not just a random polygon. So here I drew a random polygon. We could still expect to get some curves CL and CR. So random polygon is like two random pockets here, two random pockets there. And we could get some two curves here, some CR, some CL. So what would happen? We could compute those intersection points. We know that there's this gray region here. We would compute these two intersection points, P and Q, and they could look maybe like that, right? But there is no rational line through P or through Q. So actually, for this example, there would be this whole region here would be good for our middle guard, and we could find easily rational coordinates for it. Yeah, so this is bad, and so we have to think a little bit harder. So let me start with some observation. So we want that through the point P goes a rational line. And if there's a rational line, there will be at most one, because we also want P to be irrational, because if P is rational, that's not helpful, right? We want a P be irrational, but we want to have a rational line through it. And this rational line should also not go through this gray region, but that's a minor issue. And there's at most one rational line through an irrational point, because if we have two rational lines going through one point, that point is rational. So it's kind of hard to find this point having only one rational line through it. So usually you would expect to be unlucky. You could do exhaustive search, and we did do that. But I would expect you take a lot of time and all these computations to automatize. It's non-trivial to compute it. So we tried something else. And here I want to explain what we did. And so in order to understand this, you need to understand some algebra. So let's say we have a point P of this form, where R1, R2, R3, and R4 are rational numbers, and alpha is something irrational. So we need that somehow the irrational part in the x and the y coordinate is the same thing. Otherwise it doesn't work. And if we have this, then it's easy to see, that this is a unique rational line through this irrational point. And that's some simple computation. And we just chose arbitrarily alpha to be root of 2. And then in order to place our polygon, we started with the points. Because if we have the points and we can choose the shape of the points, we already know the lines that these points go through. And then we leave some stuff open for those pockets here. And then we can compute all of those pockets. And we know that these points here, because we want to have a unique solution, must be on the side of the pocket. Those points will be irrational again, and they will be again of this point, of this shape. And we can compute the lines going through, the unique rational lines going through this point. Because, so maybe we look here, we want that this point lies on the edge of the pocket. And in order to lie on the edge of the pocket, the edge needs to be rational. This means the line going through this point here must be rational as well, because this point lies on the edge. So we can compute all these lines for all 4 pockets. And usually we will be unlucky, meaning that maybe this line is vertical and we cannot produce a reasonable pocket with this line. So we play around with these parameters, so with these boundaries here and with a point there, and their GeoGebra was really helpful because you could play around with those parameters, and in real life you could see how those lines change continuously depending on the parameters we choose for all the points. So there were a lot of parameters to play around with, but the nice thing was we could observe in real time what's happening. And eventually we could find a polygon which was very nice. And in order to make this almost orthogonal, we had to try a little bit harder, but eventually it worked out. So this was very nice. And this was kind of like playing Sudoku, but it was not the same. It was a nice play. Okay. Yes, so this is how we found the polygon. I think if you want to find different polygons, you should use a similar approach, or you could use a similar approach. So I claimed another theorem that also holds for rectilinear polygons. So this is a rectilinear polygon, and the way that we do it here is we will replace all these pockets, like a normal pocket which is almost rectilinear, by some larger pocket which is rectilinear, which forces a guard on such a position that everything of this pocket is seen except what was not seen before. So we have to investigate this extra guard, but now this is exactly the boundary that we had before, and it's kind of easy to see that it's not useful to place another guard here, and yeah, then everything behaves in the same way. And yeah, and we just force 3 guards to be inside by these 3 pockets. Okay, so what are possible explanations of this, possible applications of this example? So I see 4. So the first explanation is application is that it explains the lack of algorithms. We have very, very few algorithms for the algebra problem, despite the fact that it's extensively studied and there are literally hundreds of papers on it. Some surveys have more than, I think, 1,000 or 2,000 citations, but you know, the number of algorithms are 3 or 4. It gives somehow an algebraic approximation low bound. So if you don't want to use irrational numbers, you cannot even hope for an approximation better than 4 over 3. We think it could, our example, or maybe not exactly our example, but the way we construct our example could serve as to construct benchmark instances. But we're doing theory, we're not doing practice, so we don't know if that would be a reasonable approach. And we think, or I think, maybe it could be used for teaching, but everyone that I told this idea, they said I'm crazy, So decide for yourself. Maybe it's more of a motivating example to introduce irrational numbers, getting into manipulating polynomials, rather than maybe the first example you want to see in irrational numbers. Yeah, I don't know, could be. I would like, if someone tries this in teaching, please get back to me and tell me how it worked. Okay, that was it. Thank you for your attention. And yeah, this was this joint work with Mikko and Anna, and yeah, thank you for watching.